Okay, let's do some torque problems. Okay, go ahead and pause the video. Try all 6 of these on your own. Remember, torque is force times distance of the force from the axis of rotation times the sine of the angle between those two vectors. So pause and try. Okay, hopefully you did that. You tried all 6 of these on your own. So in this first one, they give us our force and our distance, the length of the rod. Force, or the torque, will be force times distance times sine of 90. That'll give us 40 Newton meters. It's our units for torque. And that torque vector will be out of the page. So this torque is trying to make this rod rotate around counterclockwise. Imagine if you stick your thumb out towards your eyeballs and you curl your fingers around, your fingers would curl in this direction. We call that a positive torque, counterclockwise, and your thumb points out towards you. That's the direction of the torque. Okay, in part B here, it's the same scenario, but we've changed our angle. So now that we're not pushing at 90 degrees, sine of 120 is smaller than sine of 90, we'll get less torque. It's also out of the page because this force would make the rod rotate around counterclockwise. Same idea here, 30 degrees though, so we get a much smaller torque. In D, now we're trying to make it rotate clockwise. We'll get a negative torque, which will be into the page. Your thumb would have to point away from you for your fingers to curl this direction. So our torque will be force times distance. Our distance is now 2 times sine of 60. We get a much smaller torque. In E, our distance from our axis of rotation is 0. Imagine you're trying to open a door by pushing on the hinges. Yeah, you're not going to do anything. That door is not going to rotate. And F, now our angle is 0. Sine of 0 is 0. Imagine you're trying to open a door by pushing on the end of it straight toward the hinges. It's not going to open. It's not going to rotate. We get no torque. Okay, again, pause and try this on your own. Okay, hopefully you did that. In part A, we got to be careful here with that 25. Convert that to meters, 0.25. Our torque will be our force, 17, times our distance, 0.25, times the sine of 37 degrees, 2.56 Newton meters. Maximum torque occurs when you're at a 90-degree angle. You push, imagine you're literally trying to loosen this bolt, this nut. You would push at a right angle here. You would push at a 90-degree angle. Both of these would be positive torques because we're rotating counterclockwise, and that nut would come up. It would loosen. Remember, lefty-loosey, righty-tighty. So the direction of the torque is the direction this nut would move. Okay, question 2. We're moving it up a notch here. So this is a common thing we're doing in cars nowadays. We're putting in these big giant flywheels that can capture our kinetic energy. When you come to a stop, your kinetic energy is transferred into this flywheel and turned into rotational energy. It starts spinning around, and that helps brake you. It's just conservation of energy. Then when you try to get going again, this flywheel rotating around, that rotational energy is converted back into kinetic energy, and that helps get you moving. Those trolley cars in San Francisco have been using these for 100 years. Now we're starting to put these in regular cars. So we got this thing rotating. We want to know what constant torque is required to get it up to some speed. So we're going to use Newton's second law for rotational motion. The sum of the torques is I times the angular acceleration. First thing we got to find here is our angular acceleration. We have a constant torque, so we have constant acceleration. With constant acceleration, we can use our constant acceleration equations, our equations of motion. You should have those in your notes. So we use omega as omega naught plus alpha t. First, we have to convert that final angular velocity into radians per second. So that's just dimensional analysis there. Now we have our final. Our initial was 0. We started from rest. We have our time. We get an angular acceleration of 5 radians per second squared. Then we use t equals I alpha. They gave us t. We now have alpha. It would require 14.14 Newton meters to make this thing accelerate to that speed in that time. All right, 3. We got a kid pushing a merry-go-round. Again, pause and try on your own first before you listen to me. Hopefully you did. Kid's pushing tangentially. That means a 90-degree angle between the lever arm and the line of action for 15 seconds. If we're initially at rest, we want to find our final speed. So there are 2 different formulas we have for torque here. Torque is force times distance times sine of the angle, but we're at 90. And torque is I alpha in magnitude. So setting those equal, force times distance must equal I alpha. We have our force, 18. We have our radius, that's our distance from our axis of rotation to where the force is applied, will equal I times alpha. So we get alpha, is this number. And then this is constant acceleration, so we can use our constant acceleration equations and solve for our final omega. So after 15 seconds, this is how fast we'll be rotating. This thing's got a really high moment of inertia, so it's hard to get rotating. That's why we're not rotating very quickly. Okay, then how much work did that kid do? Remember, work is just change in kinetic energy. Here we don't have translational, we have rotational kinetic energy, 1/2 I omega squared. Our initial was 0, so I didn't put the minus initial because that's just 0. So our work was 100 joules. Notice here that work and torque have the same units, but they are not the same. It's just pure kind of coincidence that work, Newton meters, is joules, but torque is Newton meters. Torque is not joules. It's newtons times meters, force times distance. Okay, and then power, we want to know what's the average power. Power is just work divided by time. This kid's putting off almost 7 watts of power. All right, and then finally, this complicated one. I really, really, really like this problem. So we got this yo-yo here. We're going to let it roll down. We're told how far it rolls down. It goes down 75 centimeters. We're going to find the final angular speed and its linear speed. We're going to find V and omega. 2 different ways to do this. By far the easiest way is using conservation of energy. All of our potential energy that we start with will get converted to kinetic energy, and we have 2 different kinds of kinetic, translational and rotational. So I'm setting potential energy equals 0. I'm setting height of 0 down at the bottom, so my initial height will be 75 centimeters, and my final will be 0. The change in potential will be my translational. That's how fast the center of mass of this thing is moving. It's also how fast a point on the edge is moving linearly, plus the rotational kinetic energy, 1/2 I omega squared. So we look this up. I, for a thin hoop, we just go to our moment of inertia table, is mr squared. The key to the problem, all these problems, anytime you're using kinetic energy, is V equals omega R. So we plug that in here. So our change in height, we drop 75 centimeters. We have our mass, we have our radius. Just plugging everything in here and solving. Try that on your own. Solve that for omega. We get omega square root of GH over R squared. Notice the masses all cancel out. It's independent of mass. That's 33.9 radians per second. And then V equals omega R, or R omega. Our linear speed is 2.71 meters per second. So if this were falling down, that's how fast the cinder is falling. That's also how fast, if you put a little piece of tape here and you watch some things spin around as it goes, that's how fast that tape is moving linearly. All right, here's the hard way to do the same problem. This is the way I used to do the problem until I realized this is the easy way. So we're going to use sum of the forces is mass times acceleration, and sum of the torques is I times the angular acceleration. So if we draw a free body diagram for this thing, gravity's pulling down and this string is pulling up. So the weight's pulling down, the string's pulling up. The sum of the forces then will be the mass times the acceleration. But we also have a torque being applied that's going to make this thing rotate. Torque is the force, that tension there, times the distance, the radius of the hoop. But torque also equals I alpha. I we were given, it's mr squared. The tangential acceleration is always r alpha. So we can put all this together. I times alpha would be, there's I, mr squared, times a over r, that's alpha. And that must equal the magnitude of the tension times the radius. Okay, so now simplifying here, one of the r's cancel. We get ma equals t. Cancel out the other r. So the tension will be mass times the linear acceleration. Call that equation 1. Now we use the sum of our forces. For the center of mass here, it's going to accelerate down. We know it's going to fall. We know the weight's going to be bigger than the tension. So the tension minus the weight must equal ma. But we know acceleration is negative. So if we're thinking about the absolute value of a here, ma would be mg minus t. We need to make this positive. So that one, mg, was bigger than t. So now look at equation 1, ma equals t in magnitude, and m magnitude of a equals mg minus t. Put those together, just literally plug that t right here, and we get t equals mg minus t. That means 2t equals mg, or t equals mg over 2. The tension is half of the weight, and we get this value for the tension. But remember, tension is mass times acceleration, so acceleration would be tension divided by mass. So our acceleration is half of g. We accelerate at half of free fall speeds. Now, of course, if we had a different object here, if this were not a thin loop, we would have a different I, so we would get a different value. It's not that everything would rotate at that speed or fall at that speed, just a thin hoop. Okay, now we want to find the linear velocity, the final velocity of our center of mass. We just use our equations of motion, just plug everything in, get our speed is 2.71 meters per second, and v equals omega r, so omega is 33.9 radians per second. Same values we got doing it the other way.